So thank you very much everyone for joining today's talk. This is the second day of the Wave 14 uh, for our summer STEM school, and also this is a special talk that has been arranged in line with our effort to try to put together a Beamline for Schools team from amongst the STEM school alums. So I am very pleased today to have Dr. Pervez Hoodbhoy with us. This talk is being done in collaboration with Black Hole and is also being live streamed on Black Hole's Facebook pages. Dr. Hoodbhoy is a Pakistani nuclear physicist, mathematician, and an academic. He has earned his PhD in nuclear physics from MIT and has been a very strong advocate of scientific education and rationality in Pakistan for many years now. He's previously taught at Qaid University for over 40 years and worked on topics such as quantum field theory and black hole physics. He's very well known also for his book on Islam and science, religious orthodoxy, and the battle of rationality. Today he's going to give a talk about the physics of particle accelerators, particularly what happens at CERN, why do we have CERN, places like CERN, what do they try to achieve? And then towards the end, we're going to talk a little bit about what kind of opportunities do we have for students to do experiments at CERN. And there is a very special program at CERN called Beamline for Schools. And we're trying to put together a couple of teams to apply for that. And we would love to hear Dr. Hoodbhoy's thoughts on the subject. So with that, let me invite Dr. Hoodbhoy to the stage.
Okay.
Dr. over to you.
Okay, can you guys see me? Can everyone see me? I hope you can. यार ये बोर्ड मिटा दो अभी एक मिनट ठहर ठीक है okay. So hello everyone, I am Pervez Hoodbhoy. I'm not a mathematician, I am a nuclear physicist. I got my PhD in nuclear physics. However, it is theoretical nuclear physics, and the sort of stuff that I'm going to be talking to you about today has more to do with experiment. In fact, it'll have all to do with experiment and very little to do with theory. You know, of course, why you are here. It's because you want to go to CERN. CERN is the world's largest particle accelerator. It's huge. It's 27 kilometers in circumference. And so when I was there in the theory division, I used to live in France and then bicycle across to Switzerland. So it's a very nice place, marvelous opportunities, and I am actually quite pleased that they're giving young people the chance to go and work over there. I mean, it is unprecedented. I was there 20 years ago, and that was in theory. But now, the fact that they've made available laboratory facilities is, the intent behind that is to stimulate interest in particle physics. Of course, if you manage to go over there, you will not work in the big accelerator. The big accelerator is called the Large Hadron Collider, and that's where the really exciting physics gets done. Instead, if you get to go there, you will work in a small place which acts as a kind of support unit for the main accelerator. So this is where they test various pieces of equipment that they make. And there's also some kind of an original project over there that looks at how cosmic rays can affect the climate on Earth, which is quite amazing. Okay, so let's get on with business. यार ये मिटा दो जरा. So, what you have available to you at this thing called Beamline for Schools is actually a particle beam, meaning that from a part of CERN called the Proton synchrotron, you have high energy protons coming. By high, I mean, don't I don't mean very high, but maybe 5 to 10 giga-electron volts, which used to be enormous back in the old days, but now it's so small compared to the main accelerator. Anyway, so here comes a beam of protons. Those protons then have with them a bunch of other particles. Now, it's not that CERN wanted those particles to be there, but they're there because they came when the main proton beam hit some target, and so a lot of junk comes out. What we call junk today is what people were looking for. It was gold in those days. So back in the 1960s and the 1970s, particles like the kaon had not been discovered, but now you have this beam of protons plus junk coming along, and all this is hadrons. And this is what they're going to give you to work with. Okay, so then the question is, what is it that you can do with this? And I was thinking about it this morning, and I've come up with 4 different ideas. One of them has a very immediate application, and this would be for destroying tumors. So you know that cancer is something everyone wants to get rid of. And the conventional way of getting rid of it is through X-ray radiation. So you have X-rays which are focused upon the part of the body which contains the cancer. And because the X-rays carry energy, they go and they kill the cancer. The tumor is a little thing like this, which has got bad stuff, and which then spreads through the body and then ultimately kills you. So how do you kill that tumor? You irradiate it with X-rays, fine. But the problem with X-rays is that X-rays, as they go to the tumor, they destroy a lot of good cells on the path. And that's not good, because you kill the patient while trying to cure him. Of course, it's not that bad, but what one would like is energy to be deposited exactly on the tumor and with the surrounding tissue not being destroyed by this. So here is an idea, and it's not mine, and it's certainly now at the point where machines are being made. You use, instead of X-rays, you use a proton beam. So the proton beam, so here's some nasty tumor, and here comes the proton beam, and it zaps it. What's the advantage of the proton beam? Well, here we have to get into a little bit of physics. A proton is a charged particle. The proton interacts with the charges which are inside the atoms over here. However, if it passes by quickly, then those atoms don't get too disturbed. Yeah, maybe some of them get knocked out, but provided the proton is traveling fast, it can get through without doing much damage or without interacting much with the surrounding tissue. But it is, of course, slowing down. It has to, because it's always sharing its energy with the electrons and nuclei around it. And as it slows down, and as it approaches the target, well, its speed is such that it starts exciting the atoms around the target. And so it loses more and more and more energy until it finally, as it is close to stopping, it just, in a rush, gives most of it. So if you were to look at energy deposition as a function of distance from the target, so it comes here and then of course goes to 0 because now the proton has stopped. This is what is called the Bragg peak. And this was discovered some, 80, 90 years ago by Bragg, obviously. Okay, so a proton beam will do the same thing that an X-ray beam will do, but with less damage to the surrounding tissue. Now, even better than a proton beam would be, and this is something that is probably not available at CERN. I mean, they won't give it to you. Of course, they have lead, but that's out of the question. So suppose you have carbon-12, and you ionize it. Now, if you can ionize it, you can take 6 electrons away from that, which means that that's going to interact a lot more than a proton, which means that it's going to be a lot more effective. So this will be where it is, but the amount of energy that it will deposit will be way higher. And so if you could get carbon or nitrogen or something like that, or oxygen, then you could do a much better job than with protons. Okay, so this stuff is well known. What is it that you can do? Well, let's assume that that you have only protons available to you. In that case, you can start doing a bit of studying right now about how charged particles interact with matter, and start developing a range formula. So suppose that from this point to this point, you want the proton to stop over here. How much energy should you have in the beam so that it just crawls to a stop over here? You don't want it to go beyond because you want it to put all the energy over here. Okay, now that's not as simple as it sounds, because if this is metal, yeah, that's one thing. If it's wood, if it's another thing. If it's tissue, it's another thing. But then tissues have various densities as well. Okay? Now at CERN, they won't let you work with biological materials. They won't let you put your hand in front of it, for example. But they won't let you bring samples either. So how do you model this mathematically? And so that's a good thing to do before you go there. Okay, so that's one idea, to develop a range formula and to test this out on various materials and to create something that will help people in the future to make machines that use heavy ions for cancer treatment. Right, so that's idea number 1. Idea number 2, again, as I say, this is stuff that is known to people for a long time. The whole issue is how to put these ideas into practice and to use the facilities that you would have available to you at CERN. I'll call it channeling. So a proton beam that comes in, it's got, doesn't have one, it doesn't have 10 protons in it. It's got billions of protons in it, and they don't all have the same speed. And so some are moving up, down, and they're moving pretty fast. Actually, these protons are moving pretty close to the speed of light. And so, if something is moving even a 10,000th of the speed of light, then, and if it has an upward component, by the time it gets from here to here, it'll be way up over here. And so the beam loses intensity, and what you need are what are called collimators. So the collimator will keep it focused. Now, one kind of collimator that you may wish to think about is the following. So think of a crystal. What's a crystal? It's a regular arrangement of atoms. So, and of course it goes all the way down. What are atoms? Atoms are nuclei and electrons around them. And every charge attracts or repels every other charge. So it can be that as a proton tries to leave, because it has an upward momentum component, it gets pushed back. And before it gets here and then. Now, I'm going to ask you people to think of the following. How do you get your internet signal in the house? It's through fiber optic cables, right? So what you have is a cable that carries can be wound up in loops. How does it work? Well, light goes from here to here, is internally, it undergoes internal reflection, and of course you can't bend it too much, because at some point the light will then start leaving the cable. But this is exactly what you read in your school books about Snell's law of refraction. So provided the refractive index inside is substantially bigger than that outside, no light will leave this. So in the same sense, it is possible that a proton beam could then be carried through like this. And if you could bend the crystal, if you can bend the crystal, then you'll have something like this. So that's actually quite a nice thing. I mean, see, these protons are traveling incredibly fast. I said close to speed of light, maybe 3/4 of the speed of light or whatever. And you would think that they would just, this one would just smash through like that. But if the bend is sufficiently gentle, then the proton beam can be made to follow this. All right, so what's the advantage of this? Suppose you have a proton beam that you want to use for some purpose. And that purpose could be, for example, coming back to the cancer thing, suppose you want to target it onto the tumor. Now, one possibility is, okay, you move the patient around. You can do that because the patient is lying on a bed and there's 3D control over there. But it would be so much better if you could move instead the proton beam around. Takes away the discomfort, for one thing. And so imagine that this thing over here was a bent crystal. So then you would have this is highly exaggerated, but that's okay. In fact, you would be able to achieve bends which are much, much gentler than that only. Otherwise, the proton beam will just smash through. So this thing called channeling has been explored in the literature, and in fact, it's been experimentally demonstrated. And here is something that you could use for applications as well. Let me give you another application of that. Suppose you want to make a semiconductor wafer, and you want to deposit a particular kind of atom at some particular place on the wafer. So what you do is you take this crystal, bend it to just the right amount. The next question you'll ask is, how do you bend a crystal? Can you do it? And the answer is, yeah, you can. After all, there are piezoelectric crystals. There are, these condensed matter people know a lot more about it. But by applying electric fields, you can cause the forces between molecules to change. And so you can, through the application of an external electric field, you can get a bend, a slight bend, but that could be okay for other things. So now, you see, if you were able to demonstrate this experimentally, and if you come up with a reasonable way of bending a crystal, then you'll have hit the jackpot. It'll be very good. Lots of things that one has to think about. So, how wide should this be? Now, normally the distance between atoms in a crystal is, I use the unit called angstrom. Angstrom is 10 to the power minus 8 centimeters. But roughly, if an atom is about this big and the other atom is about this big, then the space in between is also about the same. But that's enough space for a proton to get through. It's plenty of space, in fact. A proton is incredibly small. Atoms are huge. They're huge, vast wastelands, actually. They're empty. And so a proton can just go through like that. And so that's an idea. And by the way, this would, even better than protons would be alpha particles. You know what alpha particles are? Alpha particles are 2 protons and 2 neutrons. And they could go through as well. And alpha particles would do a lot of good for the cancer, better than it, twice, not twice, but 4 times as much, because their charge is 4 times, the square of the charge is 4 times greater. So that's idea number 2. By the way, there's some people over here. If there's any question, it would be nice to have. Any thought?
Must have been done already.
Oh, yeah. Look, I'm not talking of a research problem. I'm saying that this is something that the people who are listening on to us now, if they manage to get to CERN, you see, they'll have to submit a project. The project will be evaluated by experts. And all this stuff is long known. I mean, this guy Bragg was 1900 and, I don't know, 100 years ago. The point is not that you're discovering new physics. The point is that for the first time, young people are getting the chance to work with super sophisticated equipment. And just the fact that you have a beam available to you. So it's, the difference is like that of, वो जो हम मिट्टी के खिलौनों के साथ खेलते थे ना बचपन में, और अब हम खेलते हैं स्मार्टफोन्स के साथ, वीडियो गेम्स खेलते हैं, तो इतना बड़ा फर्क है. Okay, so that is a second possibility. And then a third possibility would be measuring magnetic moments. Of various hadrons. So the stuff that comes along here, it's not just got protons, but it's got kaons and pions and muons and etc. Now, some of these particles are spinning, some are not. Whenever a particle spins, so think of the Earth. The Earth spins on its axis. Now, the Earth, by virtue of spinning on its axis, generates a magnetic field. And that's why we have the north and the south pole of the Earth. That's why all the planets in the solar system have got internal magnetic fields. And in fact, by looking at that, we can figure out what's inside those planets. But from a fundamental point of view, it's the elementary particle which we are really interested in, because that really is a signature of that particle. So take the electron, for example. It's long been known that the electron has a magnetic moment. And the electron is, you can think of the electron, I mean, this is not strictly true, but you can think of the electron as spinning on its axis. And so the magnetic moment of the electron was one of the first quantities to be measured. And I think this probably goes back to the 1930s, again 100 years old. Huh? No, this is the measurement. There was a prediction of the magnetic moment of the electron, and then there was the measurement. So how do you, at a very crude level, measure the magnetic moment of an electron? It's actually fairly simple. It's suppose you have a magnet, north pole, south pole, and you throw up an electron at it. If it is spinning one way, it'll go this way. If it's spinning the other way, it'll go that way. Anyway, the point is that at CERN, and actually that part of CERN where you might be able, where I hope you will be able to go, there is this place called ISOLD. And there they have a magnet. See, CERN works on magnets. The biggest magnets in the world, the most powerful magnets are superconducting magnets, and they have to be kept at close to 0 degrees Kelvin. Those are used at the Large Hadron Collider, and they're not even going to let you go close to them. But there's a permanent magnet, which is very powerful, or it could be an electromagnet, I'm not sure. That's got a 1 Tesla field. 1 Tesla. Okay, how much is a Tesla? It's a lot. It's a lot. It's a very powerful magnet. Now, here is the idea that this stuff, as it goes along, you put a magnet over here. You make it pass through a magnet. It's not that it's going to go up or down. That's not the point, because that deflection will be too small. But because because every spinning charged particle has a magnetic moment, what you can do is excite it. And you would excite it, so here's the proposal, you would excite it with the kind of stuff that you have inside your microwave oven. It's called a klystron. So the klystron would be placed, so this would go through a klystron. And as it goes through, the magnetic moment, so they're little magnets. Think of every spinning charged particle as a little magnet that can point either this way or this way. And it flips back and forth. It can be made to flip back and forth, rather, by giving it just the right frequency from the klystron. Otherwise, it won't dance. You see, this is what is called resonance. And this is the principle that is used in MRI, magnetic resonance imaging. You know, the stuff that you use routinely in hospitals now. It used to be called nuclear magnetic resonance. Okay, so here are these particles, some of which are spinning, others are not. What if you were to try and measure their magnetic moments using a resonance technique? I don't think this is impossible. I think it's something that you would learn a lot of good physics from. This is the core of so much in various branches of physics, where you match the external frequency, meaning the frequency of your klystron, to the natural frequency of the flip, up, down, up, down. When the two are exactly equal, or very, very close, then suddenly the flipping starts. Okay, now how do you know the flipping starts? You know, this is really crucial to bear in mind, that what we're talking about is a magnet that's about this big. All right? So a proton which is moving close to the speed of light, will be here, not in microseconds, not in nanoseconds, but in picoseconds, or I don't know what. It's very, 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 very fast. So how do you know that it's dancing? And for this, you would look at just when the klystron starts giving energy. See, you can you give energy to the klystron, and the klystron, when it is tuned to the resonance frequency there, you can in your equipment, electronic equipment, suddenly see a blip. And so in this way, you would be able to measure the magnetic moments of all the particles that are coming through. And CERN would be grateful to you, because then you could say, this is a beam that contains 85% protons, maybe antiprotons and protons will give you the same magnetic moment, unfortunately. So you can't distinguish between protons and antiprotons here. But you could have spinning mesons of various kinds. You could, I don't know the composition of the stuff over here, but whatever it is, you can tell them that it's so much of this and so much of this and so much of this for the spinning ones. So that's a nice, challenging problem. And let's see, what else to say about that? Yeah, the other nice thing is that klystrons, yeah.
Would they be looking for a unique combination of these?
Unique meaning what?
Like something different?
No, look, there's all kinds of stuff that is coming in the beam, and you would like to know how much there is of protons and how much there is of other stuff over here. And the magnetic measuring, so the klystron information will tell you something about the composition of the beam. And finally, I'll say that, look, klystrons are in the microwave region. And that's interesting for multiple reasons. Of course, there's the 3 degrees K microwave background that comes from the time of the Big Bang, but unfortunately, there's nothing you can usefully say about that from things over here. I think there was a 4th one, but I've forgotten. So I'll end
So,
over
Hoodbhoy,
here.
somebody's asking a question. What does knowing the composition of beam help with?
Oh, what does it help with? That's just for internal bookkeeping. I mean, this is not something that will result in a device. You have to be very clear. Either you do this for something which is of applied importance, or you do it because it's just interesting to do it. So in terms of applied importance, okay, so cancer was one thing that I indicated. The other thing was, what if you use, for example, channeling, which is, yeah, and use this for depositing certain kinds of atoms on a substrate? That's the whole basis of the semiconductor industry. See, we learn to handle atoms one by one, and or maybe in very, very small numbers. And so that would be another example of an application. But here, if you measure the beam composition, it's maybe it could be useful for something, but I don't know. It's interesting by itself. I just thought of it this morning. Maybe it's not important. So more questions.
So somebody has asked if a spinning charge creates a magnetic field, how does it work for planets?
For what?
For planets.
Ah, okay. Okay, let's start from this. Suppose this is a ball of charge. Let's say it's positive charge, and it's spinning around this axis. So if it's going around like that, then what do we call a moving charge? Current. Where there's current, there's a magnetic field. So currents produce magnetic fields, and hence every spinning charge will have a magnetic moment. In other words, it is a small magnet. In terms of planets, of course, it's different. The Earth is not charged. However, the Earth has an iron core. The core is conducting. And different parts of the core move at different speeds. So right at the center of the Earth, there's no motion. But as you move outwards, the iron core, the iron moves faster and faster, up to a point after which there's no iron. And that's what is called a homopolar dynamo. And it generates a magnetic field.
Guys, if you have any questions you want to ask yourself, you can also unmute yourself and ask questions. Just raise your hand. I will acknowledge you. Somebody is asking a question, what kind of crystal is being used and how do we know the right amount by which we have to bend it?
What kind of crystal and how do you bend it? Look, one way of bending it is, of course, you just put a mechanical force on it. And you bend it. Whenever you apply a force, then the atoms will readjust to a new position. And so it's, okay, think of a ruler, a plastic ruler. You take a plastic ruler, you bend it. Why has it taken the new shape? Because you applied a force to it. And in the same way, a crystal can be bent. But it doesn't have to be a mechanical force. It can be an electrical force. And so what are called piezoelectric crystals, they expand and contract on that basis. But you can also make them change their shape. In fact, if you look up the literature on channeling, you'll also learn about what kinds of crystals people have worked with. One thing I should say that it'll only work for particular directions of a crystal. So let's say that there's a crystal which is like this, okay. Now, this is an axis over here where nothing changes. It's got translational symmetry here. So it could go through, so the proton beam could channel through over here. But if you were to do it in a different direction, it wouldn't work.
Okay, there's a longish question in the chat. Safi, do you want to ask your question yourself?
Yeah, go ahead.
Safi, are you here? Okay, he's saying his mic is not working. He has a pretty long question. Let me see if I can ask the question.
Okay.
So, so he's saying what will happen at the synchrotrons? What are its restrictions? I have, I have, I have a thought experiment where a photon beam parallelly should parallelly near the relativistic proton beam to prove space distortion due to fast velocity of the beam. Is this type of experiment possible to recreate at the synchrotron? Can we interact with the beam itself, or are we restricted to only working with its emitted photons?
You talking of a proton or a photon? A, the proton synchrotron produces protons. Protons are charged
So
particles.
initially he said photon beam. I have a thought experiment where a photon beam should,
Look,
I think there's some error here near the relativistic proton beam.
yeah, it is a relativistic proton beam, but there is no such thing as a photon beam which is produced by an accelerator. Of course, a photon beam can be produced by a laser. But here we are not talking of laser facilities being given to students. We are talking of a proton beam being made, or rather a hadron beam, because it's got all this other stuff in it. So I'm not clear about the question.
Yeah, I think there's some error in the question. Next question is, what if we use channeling crystals not just for steering but also for compressing the beam to intensify relativistic effects?
You cannot compress the beam. Look, these are individual. By a beam, I mean, see, these are different particles, and they're all sort of moving together, more or less in the same direction, and more or less at the same velocity. You can't compress this. You can stop it by making it hit a target, but you can't increase its intensity. Certainly you can decrease it by stopping it, then the intensity is zero. And you can't change the speed of the particles. Where are you going to get that energy from? The speed of the particles is determined by the energy that was given by the proton synchrotron.
Any other questions, guys?
There's one from here. Okay.
Okay,
Yes,
so
please
the
go ahead.
question is,
Yeah.
can you use the proton beam identify the material that it's sort of hitting or impinging on? Let's say you have different kinds of material. So looking at how it interacts with the material, could that be one of its uses?
Oh, absolutely. One uses different targets. The beam is given to you. You have the option of choosing different targets. So, for example, suppose you want to make a particular radioactive element. You may want to do this either for research or for some medical application, in which case you will put a certain kind of atom, materials made of a certain kind of atom, and then when the beam hits it, it'll cause one element to change into another. I mean, in principle, you could change lead to gold in this way. You know, the whole idea of alchemy is now no longer science fiction. I mean, making gold is easy, except it's very expensive.
So somebody is asking if how do we target the beam to only target the tumor and not destroy other things?
Yeah, so that's the whole challenge, that if the tissue has energy deposited in it, then the tissue gets damaged or destroyed. And the whole promise of proton and heavy ion therapy is that the surrounding tissue is disturbed relatively less. And the only way, look, one way, let's think of the various ways you might do it. One is you get the surgeon to open you up and take out the tumor. But that's a terrible way of doing it, because he will have to cut through so much of your body with a knife. And you don't like that. Okay? So then you use X-rays. The problem, as I said, with X-rays is they'll kill the tumor. Why will they kill the tumor? Because those X-rays carry energy, and they are stopped by atoms within the tumor. The tumor is especially dense. So it's, it's a nodule with relatively high density. So there the energy deposition is sufficient to kill the cells in the tumor so that they don't multiply. But the problem, as I said, is that the tissue along the way also gets damaged. And because, the next thing I said was, because of the Bragg peak, you can concentrate your firepower upon the tumor itself. So it's a bit like using a sharpshooter instead of using pellet gun. क्या कहते हैं उसे? Shotgun. हाँ, हाँ. If you use a shotgun, you'll kill the tumor, but you'll also do a lot of damage.
So somebody is saying, I'm thinking of a proposal to deposit energy and produce secondary particles by interaction of the original proton beam. Is that possible? And second, how can we ensure accurate energy deposition on measurement?
On what?
It says on measurement.
Acha.
How can we ensure accurate energy
Okay.
deposition?
In terms of producing,
Energy deposition measurement. So if he wants to create a secondary particle through the energy of the photon, of the proton, then how do we ensure accurate energy deposition?
well, look, all this stuff over here, so these are mesons, this is a muon, and there's so much other stuff over here, maybe 10 others over here. These are secondary particles. They were not produced because CERN wanted them. They were produced because CERN wanted a high energy proton beam. That energy, that proton beam, I don't know how much energy it had, maybe 50, maybe 100 giga electron volts, GeV. But that's a huge amount of energy. So look, let's get one thing clear. You know, this thing comes in again and again, E equals mc squared. If you have a lot of energy, you can create mass in the form of new particles. And those particles will be of different kinds, different types. They can be neutrons, protons, pions, hyperons, deltas, anything, but only if you have enough energy to create them. Like, for example, there was not enough energy to create the Higgs or the W or the Z. You could not do that with the CERN proton synchrotron. You had to wait for the Large Hadron Collider to come about, and that took $15, $20 billion to make. So for those really heavy particles like the Higgs, you have to pay a lot of money.
So can anyone do something similar? Let's suppose in Pakistan, is there any small kind of accelerator somewhere? Let's suppose in National Center for Physics.
Oh, okay. So the question here is whether this is possible in Pakistan or not, and it is most certainly not, and will not be for the next for the foreseeable future. This is something that took European countries working together decades before they could make CERN. CERN was preceded by something called LEP, Large Electron Positron Collider. And this is the result of the most scientifically advanced countries in the world working together for decades. And they've left the United States way behind in particle physics research. So no country, even China is a part of this collaboration. And China will, they won't be able to make something as big as this for a long time to come. Of course, we're only using a very small part of this. So it's the...
So Dr. Hoodbhoy, what is the point of small particle accelerators? There are now discussions around sort of handheld accelerators and stuff like that. What are they useful for?
Yeah, okay, that's a good question. Look, there's something called a LINAC, linear accelerator, and this accelerates electrons. And these are very low energy. I mean, look, here the CERN synchrotron was built in the 1950s, or early 1960, I don't know. But that has 100 GeV. These LINACs are about 1 GeV. And so, yeah, sure, maybe less. And they're tabletop ones as well. And you say, what's the use of these? That's because they can do specific things. Like they can be used in conjunction with free electron lasers. And those lasers can then generate a lot of energy, concentrated energy, photons, mind you. So that would be one use. But the other things that they can be used for are isotope production. Okay, so you'll say, what's important about isotope production? Again, this comes from medical research. Suppose you want to know where a particular, suppose you want to know exactly where your brain tumor is located. So will they show up in an X-ray? No. Will they show up in MRI? Probably not. No, MRI, sorry, it will. But how does the MRI know? Question is, how does the MRI know? You take a particular isotope. You eat it. It goes through your digestive system. And certain kinds of elements get concentrated into tumors. Okay. Now, when they reach the tumor, they're radiating stuff. And that's where you catch them. So for that, you need particular isotopes, like technetium and molybdenum or whatever. So LINACs are used to produce those particular isotopes. I mean, you could do it in a nuclear reactor, for example. But nuclear reactors are big, expensive, security concerns, whatever. Here you have a LINAC this big, and you can produce your isotopes in your own hospital.
One more question. So there is some confusion. Somebody's asking in the chat window, when the beam hits its target, does it produce photon? Is that a wrong understanding? There is no photons that are produced?
No, no, no. Of course, it is not. It is correct. Photons are indeed produced. Actually, you cannot avoid producing photons. They're always produced. And why? Because when a charged particle hits an atom, the atom gets excited. When it gets excited, it goes to an upper level, then the photon comes down. Then the atom comes down, releases a photon. So always you're going to have photons released. But there's also another interesting thing that I should mention. Suppose you were to bend this particle around, this beam around. So yeah, like over here. Now, here's a proton that's changed its direction. Maybe it hasn't changed its speed, but it has changed its direction, and therefore it is accelerating. We know from electromagnetic theory that whenever a charge accelerates, it radiates light. Light is photons. So in the process of bending, light is emitted. That is something that's called I don't know if I spelt it completely right, maybe there are two S's, Bremsstrahlung, which means radiative emission of photons. So there's almost no way that you can avoid producing photons.
Please, if you have any questions directly. Somebody has asked, can we use test structural integrity materials which can be used for technology exposed to harmful cosmic radiation?
Can you repeat that?
To test structural integrity, improve quality of materials for satellite and other radiations.
Oh yeah, of course. These, in industrial engineering, you have to have materials of various kinds, and one way of making those materials and of testing them is by using beams to uncover some of their properties. So what we're talking about today is not some high-level research. It's very practical 21st century industrial engineering. Look, all of the semiconductor industry in the world, whether you go to Singapore or I don't think they make them in the US anymore, but okay, China, all that is deposition of atoms, kicking out atoms by focusing particle or laser beams on them. All this stuff is very practical. There's a question here.
Given that rare earths and certain minerals are in big demand now, so is it possible, since they are in very short supply, found very only in certain places, is it possible to create them artificially?
Is it possible to create rare earths artificially? The answer is, in principle, yes. In practice, it would cause your company to close down and declare bankruptcy.
So expensive.
Extremely expensive. See, today we can create any element. The question is, at what cost? And fortunately, nature has made us quite rich and made the universe quite rich. So, there's a lot of gold out there in the universe. That's because two neutron stars, when they collide with each other, they're extremely neutron rich. And that's how heavy elements, well, there's also supernovae, but when a supernova explodes, it releases an enormous amount of gold. So, maybe you don't need to dig mines, just go far enough out into space.
So how many
Saying if the beam
students are going to go?
Just one more
Sorry,
question.
just a
Yeah.
quick question.
Yeah, sorry.
So CERN is inviting students. How many and when? For how long?
I think they invited for 2 or 3 weeks, and they all expenses will be paid. It's a very nice arrangement, yeah. But of course, they have to put up a very serious proposal, otherwise they don't get selected. Okay, there's a question here, huh?
People over there.
Well, I must say that the students who were here at the black hole had no clue about theory, but they went to CERN, and I think they went there for tabligh, not for learning any physics. And it was very sad that they did that. दोबारा डायल कर लो उनकी तरफ से चलो
Which countries have more students coming?
Do we know
um,
which are the
so
leading countries?
I don't really know. You see, I have never participated in this, but I was looking at their website today, and it seems to be mostly European countries. Europe has invested a lot in CERN, and it's not surprising that most of the students who are at CERN are from the surrounding countries. In fact, when I was at CERN, I saw that there were busloads of students who would come in every weekend, and they'd show them around. And there's an incredibly interesting museum, science museum at CERN, which must be even better now as compared to earlier.
Can one visit CERN if you're in the area? Is it possible?
Yeah, they have, it's open to the public on certain days. I think in the mornings only. They don't allow you there when the main machine is working.
Okay, so students, if you have any other questions, please write down in the chat box so that I can ask from your side. So there's this question, if the beam is placed in the room with a very low temperature, can the speed of the beam particles be decreased?
No, 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 no. Look, here is something that we must know about temperature. Temperature is the random motion of some basic particles. They could be electrons, whatever. This is not random. The beam particles came in with definite speeds, definite velocities. And the surrounding area, the surrounding environment makes no difference to that. They're essentially moving through a vacuum. You can't cool down a vacuum. There's nothing in the vacuum. So remember, don't think of this as moving through air. This is all vacuum. So in no circumstances will there be a reduction in its speed or increase in its speed if you create a vacuum out. There's already a vacuum.
There's another question. Can proton beam testing help in developing radiation hardened materials for future space missions?
Yeah, but yes, the answer is yes. As a testing means, we actually, so that's really a question from material science. How do you make radiation hardened materials? So then you ask the question, how does radiation damage materials? Well, next question is, what kind of radiation? Is that radiation coming from neutrons, as would be the case in a nuclear reactor? Would it be from fast protons? Well, that's a different kind of damage that would be caused by that. And so in the case of damage from protons, yes, you would investigate how proton beams affect crystalline structure, whether they blow a hole through it, or whether, as over here, you can make them tunnel through. So yes, so the answer is yes. It is helpful in creating space materials.
Okay, and is it possible to filter out unwanted particles from the beam?
Yes, it is possible. So that's why you have collimators, and collimators can work on different principles. You could, one very simple one would be you create a little hole that, okay, will clean up your beam a little bit, but it won't remove, for example, so suppose you want to get rid of pions. You don't want pions in the beam, for example. So what should you do? Well, one way of doing that is wait, because pions, they decay into muons, and the half-life is small. It's true, the half-life is small. On the other hand, they're moving with relativistic speeds, and so time gets stretched out. You see, like in space travel, if you travel at the speed of light, you don't age, and muons will therefore, muons will therefore last longer. So the muons will decay into pions. I said it the other way around. Suppose you don't want muons. Muons will decay into pions. So filtration is possible, yes. Another way that you could do filtration is you pass it through a bend. Now, if you pass it through a bend, the heavier particles will tend to go straight. The lighter particles will bend more. And so you clean up the beam in that way too. So filtration is possible, yes.
And what actually is a synchrotron? Is it a particle accelerator?
A synchrotron is a particle accelerator, and it was invented in the early 1950s. What it has is strong. Okay, so why does anything increase its speed? How do you make a particle increase its speed? Well, one way is this. Suppose this is positively charged, negatively charged, let's say. Yeah, positively charged, let's say. Here comes an electron, which is negatively charged. What does the electron want to do? It wants to run towards the positive. Okay. Now, as it runs over here, this stops being positively charged. Instead, the next plate over here, so this is now no longer positively charged. The electron has approached over here, and now it runs towards this. But as it runs towards this switches off, and the next one switches on. So this is all synchronized, hence this is called a synchrotron.
Okay, and can we filter muons through bending using a magnetic field?
Yes, of course. So here's some fundamental physics. Suppose there's a magnetic field which is into the board. If a particle comes in and it's moving at some speed v, then it will experience a force which will cause it to bend. And you learn in books, in your, I don't know, A levels, O levels, whatever, that the force is proportional to the charge and the cross product of the velocity with the magnetic field. So a magnetic field causes a moving charge to bend. And it can be bent so much that it can move in a circle. In fact, that's how particles are made to move in circles. So if you take the CERN main ring, 27 kilometers, why are the protons moving around in a circle? Nobody wants to move around in a circle. Everybody wants to move in a straight line. Newton told us that. So why is it bending? Because there's a magnetic field. There are a few thousand superconducting magnets, massive ones, and each one of them bends it just a little bit.
The student is asking, can we bend the light to move it in a circle?
Can we bend light? Okay. I just told you. It's before you. Yeah, you can. Provided you don't make the circle too tight. So it works fine. You can bend it so that total internal reflection is not violated. And so that's a way of doing that. But of course, you can only do that with optical photons. You can't do that with X-ray photons. We don't know any way by which you can make X-rays go around like that. I suppose it may be possible in stars where, well, certainly you can do it in a black hole. Yeah, in a black hole you can do it, but probably not anywhere else.
Perfect. And the last and final question, what is the typical range of each type of particle in a beam?
What is the typical? Range.
Range.
What do you mean by range?
Energy range. Energy range.
Energy range. Okay, so the proton, K, pi, mu, all of these are, I think that if you guys get to go there, that these will be in the range of 5 to 10 GeV. They're not, it's not a monochromatic beam, meaning there's going to be a spread of energies, but it'll be, I'd say, around 5 GeV. You'll have to ask those people what it was designed for. I think you can probably go down as low as 1 GeV. And there are lots of controls over there by which they can tune the beam, many parameters of the beam. Now, one thing you have to keep in mind, so this, since this is going to be the last question, how do you, what characterizes a beam? Well, of course, the character of what particles are present in the beam, what's the energy of the particles, what's the duty cycle? See, don't think of the beam as being on all the time. It's on some of the time meaning, let's say, for 10 milliseconds, then it's off for 5 milliseconds, again 10, and so forth. So that's the duty cycle. Then there would be the spread. Well, more important than the spread is luminosity. So how many particles, well, this another word for this is flux. So the greater the flux, the greater the number of particles that cross, let's say, my hand per second. So a particle accelerator not only has to have the proper energy, large energy, but the bigger the flux, the better it is. And of course, there are other characteristics, but that's plenty for now.
Thank you so much, Dr. Pervez. It was such an insightful session for students, and I'm sure that the questions are still coming, and I will communicate all these questions to you so that the students are all set. Okay, students, are we ready for our next session? Because the speaker is already here.
Okay, so I'm done. Bye.
Thank you so much.
Thank you
sir.
very much. Thank you very much, Dr.